Okay, any questions? Now let's look at the same system in the canonical and grand canonical ensemble. Let's start with the Maxwell-Boltzmann case, which is the easiest one. Well, we need the partition function in the canonical ensemble, which was defined as, let's say, for the n particles, e to the power minus beta e, sum over all microstates of the whole system. Now, for identical particles in general, we have the sum over all the microstate we can specify by these numbers ni's. So this is actually a sum over ni's. But you see, in the Maxwell-Boltzmann case, for a given set ni, if the particles were distinguishable, let's say, identical but distinguishable, then the question is how many sets ni's we can choose among n particles. So that will be basically n factorial. This is all possible orderings, but orderings within an ni, within the number of particles in exactly the same state, will not give me a new state. Divided by product over all ni's. Now keep in mind that I'm no longer using the cells. These are single particle states. Now there's the Gibbs correction, which tells me that this should be divided by 1 over n factorial. And here the only restriction I have is that sum over ni should be equal to n. This is the only restriction I have. In the microcanonical ensemble, the energy is also fixed, but in the canonical ensemble, energy is not fixed, but the total number is fixed. And then, of course, I also have e to the power minus beta. The total energy in terms of these ni's will be just epsilon I and I. Well, let me just keep the n factorials as they are. So Qn is 1 over n factorial, sum over all possible ni values, subject to this constraint. Let me put a prime to denote the constraint. And then I have a product of e to the power minus beta epsilon I to the power ni divided by, well, here I have ni factorial divided by ni factorial. And there's also n factorial. This is 1 over n factorial sum over e to the power minus epsilon I to the power n. Do you agree? It's not the binomial expansion, it's the polynomial expansion. So let's do a few cases. A plus b squared, this is the binomial expansion of squares. This is a squared plus twice ab plus b squared, which I can write as 2 factorial divided by 2 factorial 0 factorial a squared plus 2 factorial divided by 1 factorial ab plus 2 factorial divided by 0 factorial times 2 factorial b squared. Well, the first term is the factorial of the power of a. The second term is the factorial of the power of b in each one of those terms. And for each one of these a's and b's, each one of these factors, I have a corresponding factorial. Well, let's go back. Everything has that 2 factorial. In the general case, it will be n factorial. And I have the products of various terms. Here the terms are a and b. And each, let's say, let me rewrite it slightly differently. This is 2 factorial, a squared over 2 factorial, times b to the 0 over 0 factorial, plus 2 factorial, a to the 1 divided by 1 factorial, b to the 1 divided by 1 factorial, plus 2 factorial, a to the 0 over 0 factorial, times b squared over 2 factorial. This term over here is just a generalization of this one. Here I have just the sum of 2 and 2 terms, so each term contains only the products of 2 factors with various powers. Here I have, and the sum of those powers, 2 plus 0, 1 plus 1, 2 plus 0, they are all 2, the overall power over here. You see here I have products of various terms with their powers. Each term is also divided by the factorial of the power, and the sum of the powers is fixed to n. So it's just this, if you just take the nth power of this sum, this is what you would get. And well, this is, here I'm summing over all I, all the single particle states, but that is nothing but the partition function of a single particle. Well, this is what we had used very frequently. And this, for the free particle Q1, remember, if you remember, this is nothing but e to the power minus beta epsilon squared, not beta epsilon, d cubed p, d cubed q, divided by h cubed. And this is actually v over lambda cube. Now this lambda is almost the lambda that we had defined last week. Lambda is h over 2 pi m kt to the power 1/2. This is called the thermal wavelength. Well, why it's called a wavelength? Well, let's just imagine one particle in my system. It has a momentum given by square root of 2me, E being its energy. Well, the average energy of a single particle is 3 over 2 kT. So 2's will cancel. This is equal to 3 mkt to the power 1/2. Typically, these are typical values. Well, for a given momentum, there is a corresponding de Broglie wavelength, h over p. Well, this is almost the same thing as this expression. Well, the factor over here is approximately 6. Here it is just 3. There's just a numerical difference between those two factors. So, but nevertheless, they correspond to typically the same thing. And what that is you see, due to their thermal motion, all of these particles has a momentum and hence a de Broglie wavelength. So the de Broglie wavelength is kind of the size of these particles. So if you would like to assign a size to a quantum mechanical object, that size would just be the de Broglie wavelength. So if you look at over here, Q1 in this sense is just the number of these units that you have in your system. So each particle has a size which is given by the de Broglie wavelength. So it has a volume given by typically the cubed of the de Broglie wavelength. So V over lambda cube is essentially how many of these you can fit in your volume V. This is your Q, the single particle partition function. And in fact, classical limit would just correspond to the case that this is large. Because if this number v over lambda cube is small, various particles will start feeling the quantum nature of the other particles. And hence quantum mechanical effects will start to be important. Okay, so now we have Q1. So Qn is just 1 over n factorial v over lambda cubed to the power n. And well, now we can calculate the grand partition function also. This is the n particle partition function. The grand partition function, which will be a function of, let's say, z and v and t. This is z to the n qn, and from 0 to infinity. And keep in mind that z is e to power beta mu. And this is sum over n 0 to infinity, z times v over lambda cube to the n times 1 over n factorial, and the Q potential, which was a PV over KT, which is the logarithm of Q. Now this is, by the way, exponential of ZV over lambda cube. This is just ZV over lambda cube. Or the pressure, if you like, ZKT over lambda cube. Well, we can look for the number of particles. Remember, dq was minus TdS plus PdV minus n d mu. Right. Now let's go back. All are minus. No, this is plus. So n is minus dq by d mu. Sorry, this is not SDT. At constant temperature and volume, this is equal to, I made a mistake somewhere. Let me check. So this should be plus, I think. So this should be plus. So this is plus. Q is just derivative with respect to mu of z v over lambda cube. Derivative of z with respect to mu is just beta z. Because keep in mind that z is e to power beta mu. So if I take the derivative with respect to me, it just brings a factor beta. So let's see, z times, now what I'm trying to do is, here I have the pressure, or if you like, here I have the PV over KT. This is equal to Q. But this is also the same thing as n over beta. You see, when I take the derivative of Q with respect to mu, I get Q, this is Q, multiplied with beta, which is n. So n over beta is also Q. There's a mistake somewhere. Oh, sorry. The mistake is over here. This is not Q. This is Q times KT. PV over KT is Q. Okay, let me go back. Okay, PV over KT is Q, which we had defined as e to power minus alpha minus beta epsilon in the case of the Maxwell-Boltzmann particles. And this sum is over, let's go back. This is not Q. This is just E minus Ts minus Mn. Which is minus KT times Q. Okay. Okay, so now, what else do we know? What is N? N was sum over single particle states of 1 over e to the power alpha plus beta epsilon I plus A. Now for Maxwell-Boltzmann, let's specialize with for simplicity, PV over KT, again A goes to 0. As A goes to 0, this A goes to 0. Here we have the logarithm of 1, which is also 0, 0 over 0 uncertainty. So you can just take a limit. This is sum over single particle states. Of e to the power minus alpha minus beta epsilon I. But this one, as A goes to 0, is also sum over single particle states of e to the power minus alpha minus beta epsilon I. So this is nothing but N. So PV is equal to NKT. Now, one interesting thing of this result, okay, we had derived this result many times using different approaches, but here, for example, this doesn't really depend on the fact on what the values of epsilon I are. Whatever the energy eigenstates of my system are, PV is equal to NKT. Of course, in the limit that Maxwell-Boltzmann distribution is applicable. Now let's go to the other distributions. The canonical ensemble of the Maxwell-Boltzmann or Fermi-Dirac. Well, the starting point will basically be the same. Whatever the distribution is, this is our partition function. This will be equal to sum over the microstates. Well, the microstates will again be determined by ni's. The total number is fixed. But as long as the total number is fixed, whatever sets ni has the same total number, it should contribute to the sum. And each set ni contributes a single term to this sum. Because since they're identical, just exchanging those particles will not make any difference. They don't give me a new microstates of the system. Of e to the power minus beta, sum over ni epsilon I. Now, in the book at least, the author inserts some statistical factor, g and I, and he says that, okay, this g and I is equal to 1 for bosons and 1 for fermions and ni is equal to 0 or 1. 0 for fermions if any ni is larger than 1, and 1 over n1 factorial, n2 factorial, etc. for Maxwell-Boltzmann. It basically takes into account all possible cases. Now the problem in here, well, for the fermions and bosons, we have this Qn sum ni prime e to power product of I e to power minus beta epsilon I to the power ni, keeping in mind that the prime now means that the sum of ni's should be capital N, the total number of particles, plus each ni for bosons, they can be any number, but for fermions ni is 0 or 1. Now there is no simple way of calculating this sum. But what we do is we go to the grand partition function. You see, grand partition function is sum over n from 0 to infinity of z to the power n of the partition function, canonical partition function, which is sum of n from 0 to infinity z to the n but n is also nothing but sum over ni. Sum over n and then sum over all these sets ni subject to the constraint that their sum should be equal to capital N of z to the n, but n is now sum over ni, product over I e to the power minus beta epsilon I to the power ni. But now the sum over ni with the constraint that their sum should be equal to capital N, and then the next sum over the capital N basically just gives me a sum over all ni without any constraint. Because basically if I don't put any constraint, the sum of the ni can take any value and each one will contribute. Well, when I'm imposing the constraint and summing over the sum of the ni, I'm summing over all possible sums. of product of I z times e to power minus beta epsilon I of ni. Now, each one of these sums over the various, for example, there is a sum over n0 ranging from sum over n0 of z times e to power minus beta epsilon 0 raised to the power n0. Then there is a sum over n1 and the e to power minus beta epsilon 1 to the power n1 and so on. You see, I have multiple sums over there. I can just imagine, let's say, summing over n0, sum over n0 to be the innermost sum. But when I sum over n0 of z times e to power minus beta epsilon 0 n0, it's independent of the other sums. So I can just factor it out of the sum. Then I can just repeat it for n1, for n2, etc. So those sums over sum over n0 is independent of the other sum, so I just factor it out of the remaining sums. Then the sum over n1 is independent of the sum over the other sums, so I just factor it out of the remaining sums, etc. And at the end of the day, I just get the product of sums. Now, of course, each one of these n0s and n1s, they will have different values depending on whether I'm talking about the bosons or fermions. For fermions, the sum is just, and each one of these ni's can take only two values. So they are either 0. If n0 is 0, then this term is 1. Or they are 1. If it is 1, then it is the contribution is z times e to power minus beta epsilon 0. And keeping in mind my convention of a's, you see A was minus 1 for bosons, plus 1 for fermions. Let me just add the A over here. At least for fermions, it gives me the correct expression. For fermions, A is just 1. And N0 takes the value 0 or 1. Well, for bosons, N0 can take values from 0 to infinity. And then the sum is nothing but 1 minus A times Z. 1 minus z times e to power minus beta epsilon 0. So both for fermions and bosons, these are both a's. Whether it's a fermion or boson, that sum is always 1 plus a times z e to power minus beta epsilon 0 to the power a. And similarly for the other ones, n1 sum will also give me 1 plus a times z times e to power minus beta epsilon 1 to the power a, etc. So now I have my grand partition function. Ordinary partition function, as I said, for fermions and bosons, I mean, there's no simple trick. There's no closed form, but for the grand partition function, we can easily evaluate it. And then the Q potential, if you remember, this was nothing but the logarithm of the grand partition function. This is just a times sum over logarithm of 1 plus a z e to power minus beta epsilon I, sum over all single particle states. So now we have the Q potential for my system. And just keep in mind, A is 1 for fermions, 0 for bosons. No, minus 1 for bosons. And so now we have everything. Well, let's get several, For example, what is the average number? Well, keep in mind that Qn, grand partition function, was sum over n from 0 to infinity, z to the n times ordinary partition function. Average n is nothing but n from 0 to infinity, n times z to the power n Qn divided by n from 0 divided by the grand partition function. This we can write as the derivative of n from 0 to infinity of z to the n Qn, derivative with respect to z times z, and then divide by 1 over the grand partition function. Now when we are taking this derivative with respect to z, we are keeping the temperature constant and the volume constant, because this we are not differentiating this Qn, and that Qn depends on T and V. It doesn't depend on Z. So we need to take the derivative with respect to Z, keeping T and V constant. So an average is Z times the derivative with respect to Z of logarithm of Q, or Z times derivative with respect to Z of the Q potential. Well, we already have the Q potential. Average n is Z times the derivative with respect to Z of this term, which is Z times A times the sum over single particle states. Well, if I take the derivative with respect to Z of this one, that becomes 1 plus, no, there's no 1. A e to power minus beta epsilon I divided by 1 plus az e to power minus beta epsilon I. Well, a is either plus 1 or minus 1 in this case, so I can just cancel these a's. A squared is just 1. This is equal to sum over single particle states of 1 over e to power z inverse e to power beta epsilon I plus a. And this was nothing but, if you remember, Ni star over Gi, number of particles per state. So that's kind of expected. What about the energy? Average energy of my system. Well, again, let's just remember what this Qn was. This is sum over n of z to the power n, sum over e to power minus beta e. So now, average E is sum over n, z to the n, sum over e to power minus beta e, 1 over the grand partition function. This is 1 over the grand partition function. If I take the derivative with respect to beta, with a minus sign, it just brings this factor e. Of course, when I'm taking this derivative, I need to keep z constant and v constant, because I'm not taking the derivative of e of q E, the average energy is minus the derivative with respect to beta of the Q potential at constant Z and V. This was the Q potential. Well, this is equal to, if I take the derivative with respect to beta, A times sum over single particle states okay, I'm keeping Z constant. 1 is a constant, A is just a constant. Since I'm keeping the volume constants, epsilon i's do not change. It's just this beta over there. When I'm taking the derivative with respect to beta, it brings down a factor epsilon I, minus epsilon I, but there's a minus sign over there that also cancels. A times Z times e to power minus beta epsilon I, divided by 1 plus A times Z times e to power minus beta epsilon I. Again, A squared is just 1. The average energy just turns out to be sum over, again, single particle states of epsilon I over Z inverse e to power plus beta epsilon I plus A. Again, compare this with term over there. Well, if you just look at that, this, as I said, this is the average number of particles in a single particle state. If I multiply the average number with the energy of that single particle state, I just obtain the average energy in that single particle state, but that is just this one. If I just sum over all single particles, sum the average energy in each one of these single particle states, I get the total average energy. So kind of everything turns out to make sense, let's say. Now then, if you like, the classical limit, or the Maxwell-Boltzmann limit, is the limit that A is 0. Yeah, the Maxwell-Boltzmann case, not the limit, corresponds to A is equal to 0. Or A is negligible compared to the other term. So both correspond to the same, mathematically they correspond to the same thing. Either A is equal to 0, or the term that we add to A is much larger compared to A, so we can ignore A. Now, for fermions and bosons, we cannot really say that A is 0, they are 1 or minus 1. But we can still say that in the limit that term, Z inverse e to power minus beta epsilon I is much, much larger than 1, in that limit, we can basically ignore A. But A is the term that differentiates the Maxwell-Boltzmann particles from fermions from bosons. So this is actually what we mean by the classical limit. Or this is, in fact, e to power epsilon I minus mu. This should be much, much larger than 1. This is the definition of the classical limit of the statistical systems. Now, for large T, at high temperatures, so we can still talk about the classical limit. We have seen many cases where the large temperature, well, you see, when we have the large temperature, we said the thermal de Broglie, the thermal wavelength will be small, because the momentum will be large, so the de Broglie wavelength will be small typically. So that the particles will not really feel, if the density is not high enough, the particles will not really feel each other. There's quantum nature. So large temperature limit should kind of correspond to classical limit. Combined with this result, this basically tells me that mu is large and negative. At large t. Because otherwise you see mu is large, t is large, so that ratio need not be large. If mu is small, not large, mu over epsilon minus mu, at least for some epsilons, will not be large, it will be small. And hence it won't be much larger than 1. So at least some particles in my system will not behave classically. The only way to guarantee that all particles are behaving classically in the large t limit is when mu is large and negative. Negative meaning that smaller than the minimum value of epsilon I. The ground state energy we can just fit to 0, so anything smaller than that is negative. In that sense, mu should be negative. But if it is behaving classically, you see, we had already seen that n is. So here what we did was, if you remember, we had said that for classical particles, at least Qn is Q1 to the n factorial, Q1 to the n divided by n factorial. Grand partition function was exponential of z times Q1, but Q1 has a dependence on volume. Just think of ideal gas, they are free to be anywhere, so there is a volume dependence, an overall V dependence, and some function of T. Well, then we know what the grand partition function is, what the Q potential is. We can obtain the total number as ZV times f of t. And for the ideal gas, f of t is just, for single particle, 1 over lambda cube. So Z, which is n over V f of t, which is n, the number of particles, well, let's just keep it n. N over V times lambda cube. You see, if mu is large and negative, Z, which was e to the power mu over kt, should be much, much larger than 1. Sorry. Much, much smaller than 1. Because mu is negative. But at the same time, in the classical limit at least, z is just n times lambda cubed over v. So this should be much, much less than 1. Or v over lambda cubed, which should be much, much larger than n. This was basically one of the criteria we use for the classical limit. Now we have derived it. If this condition is not satisfied, well, we can also write it in this form, n lambda cube. You see, lambda cube is the typical thermal size of my particles making my gas. If I multiply it by n, I obtain the total volume occupied by the thermal volume size of my objects. The total volume occupied by the thermal size of my objects should be much, much smaller than the total volume of my objects. This is basically the criteria for the classical limit. And before we had just stated it, now we had actually derived it. Because in this limit, basically this first term is much larger than A, so we can just ignore A. So the distinction between the fermions, bosons, and Maxwell-Boltzmann particles just disappears. Of course, we will be more interested in, so if they deviate, what are the differences? Okay, any questions? Okay, then see you tomorrow.